I will now try to wrap up the presentations we have seen during the last 2 days, also the breakout sessions, and to highlight some of the developments of Geodict, and also give a glimpse into our roadmaps for future developments. So this slide was the first slide that has been shown on this conference by Andreas Wiegmann. How do you develop a new material? There's the experimental approach. You do prototyping, you find maybe your process parameters, you manufacture the material, you measure it, and you measure the physical properties. And you have to continue this loop until you find your desired material with the desired properties. If you want to do that digitally, you need to start with an image of the material, usually something like a CT scan. And then this 3D image needs to be processed until you have something that is called here a voxel mesh. In Geodict, we often call that a structure, since we rely on voxels. And based on this voxel mesh, you can do simulations and compute the physical properties digitally. And we also have these structure generators, and you can create digital models, and you can try to run this as a loop for parameter optimization, design new models digitally, generate the structure, and simulate the properties until you have found your desired material. And of course, when you do that digitally, it's very cost effective. You can save resources, you can save a lot of time. So there are many advantages. But of course, what you do also needs to be validated. So you need a validation compared to your experimental result. This is also very important. And when you have done that, the digital model that fulfills your wanted properties then is your next generation material. And if you have ever asked yourself why we call Geodict the digital material laboratory, this is the answer. Because it's not only about image segmentation or not only about numerical simulation. We want to deliver the whole lab to you. Like you have the experimental lab, we want to deliver you the digital lab. And so we have these 3 pillars. We have image processing, image segmentation, analysis, but also the digital modeling, so geometry modeling, the so-called statistical digital twin, and also the possibility to export these materials again to other software. And there's the 3rd pillar, the property simulation, the simulation of physical properties. And we packed that together for you in a professional GUI and also post-processing for visualization. And because in the end, like in this talk, if I want that someone else understands me, understands what I have found, I need to somehow visualize my results. So that's also very important, and that's also a great strength of Geodict. And of course, we also have the automation and the scripting possibilities to complete your digital lab. So when it comes to image processing, you have learned in this conference, for example, that for fiber materials here on the top left, you have the possibility to identify binder in a CT scan and differentiate the binder from the fibers. You can also use AI for that, which is very powerful. You can identify single grains in a granular material and get the properties of each individual grain and statistics, for example, of the size distribution of the grains. You have seen the magic brush for AI segmentation, which is also very powerful. Then another example on the bottom left, the thickness estimation for structures, which is also very helpful. And on the bottom right, the identification of single fibers. Yeah? And when I started today in the opening talk, I said, well, to measure the fiber length of a non-woven, this can't be done in an experiment. This can only be done digitally. So what we see here, to really simulate or retrieve the fiber length distribution in a non-woven material is really a unique possibility which digital material design delivers to you. And we also showed you a lot about the possibilities we now have with artificial intelligence. You can directly identify grains in CT images with AI, find grain contacts in center points. You can use AI to improve the image quality via super resolution. And we have a module, GeoDict AI, which actually gives you the possibility to train your own neural network based on your individual training data. So if you have certain requirements regarding identification of certain objects that your material has, you can train your own network, which does the job perfectly. And when it comes to training data, of course, GeoDict can be a very powerful source of generating training data to train your own neural networks for various applications. Let's look at the second pillar, digital modeling. So we have very powerful structure generators in GeoDict, and we're very proud of that. There's, I guess, maybe no structure that can't be generated with GeoDict. You can generate, for example, gas diffusion layers for fuel cells, solid oxide electrodes for solid oxide fuel cells, for example, filter bleeds, non-woven materials, filter media, anodes, electrodes for batteries, and also catalyst layers, so fibrous materials, granular materials. There are huge possibilities how you can use GeoDict. So what is actually a statistical digital twin? We often use that word, but maybe it's still hard to grasp what we mean by this. And there are a lot of definitions for digital twins. So digital twins can be a lot of different things, depending on what you mean. You could have a digital twin of a real physical object that maybe also is updated with live data. For example, you can have a digital model of a digital twin of a car, to see how the car behaves in reality, and it is updated with real-time data, etc. But when we talk about a statistical digital twin in GeoDict, what we actually mean is the set of parameters, of statistical parameters, that we use to generate a microstructure that has similar physical and geometrical properties compared to the real material. And if we have determined these properties, then we can recreate the material as a digital twin. We can create thousands of them, and every new model that we create will again have these statistical same properties. And this is the base for the design of a new material. As you see it here, it starts with the material itself, of course. You collect the image data, you process the image data in GeoDict, segment the image, and then rebuild the material as a digital twin in GeoDict. So what did we improve or what are we aiming for? Yeah, for the twin generation, we have the possibility, for example, for granular structures, so that you, with grain find, you can analyze a real material, and then you can just load the GDR file into GrainGeo and create a statistical digital twin. Yeah, for fiber materials, that's not so easy, but we are working on it. And here you can see this workflow we are currently working on, so that we can actually, or that you can easily also create a digital twin for fibrous materials just within a few hours automatically, instead of manually tweaking the parameters for hours until in FiberGeo you finally have gotten out the desired digital twin structure. And as you already have seen in the talks, I think a lot of time, and it was really discussed a lot. Yeah, so we think there's a lot of attention on this. 2D to 3D digital twin. Yeah, we now have the Geo app for granular materials only. You can start with a segmented 2D image. You can load that into the Geo app, and the Geo app will, based on this 2D image, retrieve the properties and create a 3D digital twin via optimization loops. Okay, let's come to the third pillar, the property prediction. What you have seen on this conference is that we are working on helping you to also simulate the charging behavior of solid-state batteries, to do some research on that topic. We have learned that you can also simulate electric charge infiltration, which becomes very important in filtration nowadays, for example, for air cabin filters. We have learned that when you do an MICP simulation, then sometimes it's important that you not only simulate the mercury intrusion, but also the mercury extrusion. And you have learned that with Geodict you can also evaluate the lithium plating potentials in a battery to reduce aging of the batteries and to understand in general how the battery degrades and ages. We have now also added viscoelastic materials to Geodict, and you are also able to simulate adsorption. So what we plan for the future is to make our Lear solver even better. We're constantly working, and we are very proud of the Lear. And we're currently working on also improving the adaptive grid of the Lear solver and adding subvoxel resolution. So this will enable us to do faster flow simulations, also with high Reynolds numbers. And we are also working on large eddy simulations, because these large eddy simulations, they are much cheaper than if you do a simulation on a finer grid. So here you see the large eddy simulation, the LES, in a little sketch. And we are also working on solute transport. This will be and for Geodict 2026. So in the future, we are also planning to add aqueous reactions. That's so that solutes may react with each others. and also mineral reactions, so dissolution and precipitation of solid phase affecting the solute composition. So we already have a prototype in GeoDict 2024 for detachment of contacts in Elastodict. This is at the moment a GeoApp, and you can see here a small example how detachment now works in GeoDict. You need to define a penalty factor between 0, which is no resistance, and 1, so that no detaching is possible. And my background is batteries, so I know that for battery degradation, this mechanism of detachment is very important to deliver an accurate simulation. And of course, we will include, or we will keep on working and to include this fully into GeoDict very soon. And also, we are currently working on large deformations due to thermal expansion. And this is a very nice video done by Eric Klatt, where you can see how this structure deforms due to thermal expansion. Okay, so now at the end, I also have some roadmaps for you to give you a glimpse what we are working on. So for the filtration business area, we are currently working on electrostatics. And as I said, electrostatic decay, different charging modes for fibers, and also, of course, the validation of this simulation approaches. It's very important, for example, for cabin air filters, room air purifiers, face masks, etc. And we are also working on adsorption, implementation of Langmuir and tooth adsorption isotherms, and the implementation of linear driving force models. Activated carbon capture, this topic is also on our roadmap. And we are currently also involved in a project where we work on coalescence. Here we need to validate the experiments from our project partners. And this is important for air and oil separators and fuel filters. And we also continue on working on the complete filter simulation, usage of several outlets, and also the implementation of the large eddy simulation. And this is important for the simulation of turbulent flow regimes. In the electrochemistry business area, so batteries, fuel cells, electrolyzers, we work on concentration-dependent parameters in active materials. So this is very important to be able to really compare a charging simulation to real experiments, because the material properties, they depend very much on the actual lithium concentration we have in the active material. And for fuel cells, we are working on delivering to you the better possibilities to do saturation simulations on models that have different scales, and that's a big challenge for fuel cells. You have the GDL, and usually the catalyst layer is much smaller in dimension. So the structures of the catalyst layer are much smaller. So we need the possibility to do better simulations on different scales. And we are also working on water condensation in GDLs. so that you can simulate that. And as I already said, we try to improve our models for solid-state battery simulation. For the digital materials roadmap, on the short term, we want to enhance the mesh export and the export to other software. Then the automated statistical digital twin generation for various material types, as I said, for example, for fibrous materials, and the detaching of the contacts in mechanics simulations. And on the longer term, object recognition in grayscale images via AI, and the AI upscaling of gray value data for more efficient usage of imaging equipment, and the enhancement, computation of larger deformations in mechanics for highly porous materials, so better mechanical simulations on porous materials. And also sliding of objects in mechanical simulations, which is also very important, especially when you have detachment, then of course the objects, they can also slide in simulations, or they should be able to slide in the simulation. And finally, we come to the DRP roadmap. On the short term, we want to deliver effective properties on the medical CT level, the Darcy scale, to you. We want to enable you to compute P and S wave velocities, and also 3D rock properties from 2D thin sections. And also we want to advance with the Lia solver for geomechanics. On the longer term, we want to improve the potentials for CO2 trapping simulation. And we want to advance the Lia solver for geomechanics, compressible fluids, frequency dependency, and also improvements for artificial intelligence, for image processing and segmentation and grain identification in the digital rock physics field. So, thank you for your attention. And of course, I'm happy to answer your questions.